Hi there, passionate people. In this video, I'm going to talk about some examples of uniform circular motion. And main objectives is to understand how to apply Newton's second law, believe it or not, Newton's second law to uniform circular motion and understand apparent weight and weightlessness. Not weightlessness, apparent weight. We'll get to weightlessness later. So we can apply Newton's second law to uniform circular motion as well. We already discussed for a uniform circular motion, we have circular motion around a circle. Velocity is always tangent to that circle. Its magnitude or speed doesn't change, but its direction always changes. Thus, there's an acceleration causing that perpendicular to that velocity and towards the center. And we also discussed that there should be a net force towards the center because there's an acceleration. Whenever there's an acceleration, there's a net force. So that already brings the idea of Newton's second law. If there's a net force, we apply Newton's second law. F net is equal to ma. And guess what? We can apply it here too. And since we learned that A is equal to V squared over R for uniform circular motion, we can input that here. And we're going to have this equation for F net in a uniform circular motion. This will be the star of the show for this part. F net is equal to mv squared over r. So what we're going to do will be the same as we applied in the second law. We're going to find all the forces in the system, add them up, find F net, add them as vectors, remember, and then we're going to calculate whatever we need to calculate, and that F net is equal to ma or mv squared over r in this context. The force is also center seeking, looks toward the center, is called centripetal force. That's our F net, not a new force. It could be a tension or a normal force depending on situation, friction force. But we call it centripetal because it's always towards the center. We don't have to call it centripetal, but it's called, and you'll hear it in the book and here and there. So I just want to give you that context as well. It's a net force, and it's always towards the center. Okay, that's the main idea. Centripetal force and centripetal accelerations are always towards the center. That's why we call them centripetal force and centripetal acceleration. They are not actually a new idea. Here's what we will do as we are solving dynamic problems of circular motion or circular motion with an F net is equal to ma. We will, of course, as always, draw an ugly picture. Examine the physics in the problem, mean and write down everything you have, show all the forces and so on and so forth. List all the variables and then apply Newton's second law. F net is equal to ma. Again, in this context, this will end up being mv squared over r because A is equal to v squared over r. And I'm hoping that everybody's on board with the idea that r is the radius of the motion, circular motion. So in this picture, it will be this length here. And v is the velocity, always tangent to that circle. And m would be, of course, the mass of the object. Well, this is a force, unit will be in Newton. Let's remember those as well. Mass, that would be kilogram in SI units, and R would be meters. Remember, again, unit of velocity is meters per second, and we get Newton for the force. Here are some situations, different situations for uniform circular motion. We could have a horizontal motion like in this first figure here. Then we will have tension towards the center. That will be our force, that will be our F net. We'll say F net is equal to ma and v squared over r. And we can directly calculate it, simple as that. If we could also have a vertical circular motion, which is a bit more complicated. If I am, for example, rotating this bucket instead of horizontal, vertical, at each point along the motion, I will have a different tension because mg and tension directions will vary. If I'm at the bottom here, as you see in this figure, mg is down, tension is up. So I'm going to write down my F net is equal ma equation. I'm applying this to here, and F net is mv, which is mv squared over r, right? F net will be all the forces added, and my net force for a uniform circular motion is always towards the center. A is towards the center. Remember, we always take the direction of A to be positive. So in this picture here, we will take always towards the center to be positive, okay? Because A is always towards the center. And then we name our forces as plus and minus. T will be plus in this case, mg will be minus. So if I write down my F net at the bottom of this vertical motion here, I will have T, which is plus minus mg, equals ma or mv squared over r. And then I'm going to solve for t. They gave us the values along here. And so I solve for t, it will be mv squared over r plus mg. On the sides, we will only have t. Mg will be maintained by air friction. And t will be F net simply mv squared over r along horizontal. At the top here, let me write that down too quickly. I have T and mg down, so both are positive towards the center, positive. No other forces, so I'm going to have here T plus mg equals mv squared over r. I shorten this a bit here. F net is equal ma is where we start from, right? A is v squared over r. We find our F net and at. Similar situations, it gets a bit complicated in this case here. This is also a horizontal kind of or mixture motion here. We have this object rotating along horizontal, but look at the tension. Tension has an angle within horizontal. So since I have the uniform circular motion along horizontal here, I'm looking at the force that looks towards the center, and I'm interested in that force. That will be my F net is equal ma. Okay, and that's my Tx. I don't know why they would say Th, Tb. And Tx, so F net is equal ma, I put here, and F net is only Tx. I'm taking that as positive again because I know A would be towards the center everywhere and so on. So that direction towards the center direction simply is always positive for a uniform circular motion. And Tx is equal mv squared over r will be our approach here. What is Tx? We know, right? Tx is equal to T cosine theta. Remember, we always find the angle with the horizontal, and x component is the force times the cosine of that angle. This is a similar situation to that one we have over here. Actually, I'm gonna delete this guy from the top. In this situation down here, we have vertical motion, and difference is instead of tension, we have normal force. So we're going to show our mg, and we're going to show our normal force everywhere. Let me show mg here. Everywhere. And the normal force will be always perpendicular to the surface. Remember, I'm going to call this N here. We can also call it Fn. Always perpendicular to the surface. And we will pick the towards the center positive. So these guys are positive. This is positive, positive, positive. Here mg will be negative. And on the sides, we're also going to apply F net is equal to ma. I have another question on that. I'll leave it at that. But let me do the top only here. On the top, I have N plus mg. and that's equal to mv squared over r. Look how it is similar to what we had here. Instead of tension, we have n, that's all. And when we solve for n, we will have mv squared over r minus mg, and that's it. Please play around with this and solve for n at any point, similar to this guy over here. These are really, really similar. Okay? And this dude here is simply the same as the one on the left. Vertical motion for uniform circular motion wise, I would be interested in this part of circle. And we'll do some examples on that. These are all the types of questions we might see. And look, the idea is always the same. F net is equal to ma. And a is v squared over r. Here's a question. The model airplane with a mass of 0.9 kilograms, so this guy has a mass, velocity is shown, I'll leave it as is, and that mass is 0.9 kilogram. Okay, in figure below, moves at a constant speed on a circle that is parallel to ground. That tells me it's horizontal, no angle with this tension, so it's a simple matter. I have tension towards the center. Since my velocity is always changing, that's t, not plus. Let me try that again. This tension. I'll take the plus towards the center because I know acceleration is always towards the center. That's my plus. All right, the weight of the plane is balanced by the lift generated by its wings. Imagine here we're looking from bird view. We're seeing this from the top. mg is down and it's maintained by the wings lift. So we're not interested in that. We're only interested in this horizontal motion. Along the horizontal flat surface here, I only have tension. When I apply F net is equal to ma, which is mv squared over r, uniform circular motion, my F net will only be t, and that's it. T is equal to mv squared over r. The weight of the plane is balanced by the lift generated by its wings. Find the tension in the string if its length is 1.7 meters. What would be the length of the string? The radius, right? So the guy is in the center. I'm going to draw it in this direction to make it more clear because we already drew something there. The guy is in the center, and there is a distance from the guy to the plane, which is the length of the string. That would be our r. So r is given as 1.7 meters. And the speed of the airplane is also given as 8 meters per second. What is the tension? All we have to do now is to input these values. So the tension will be 0.9 kilograms times 8 meters per second. This guy should be squared divided by r, which is 1.7 meters. And that should give us a tension of 33.88 Newton. I actually am gonna go ahead and call this the force of tension from now on, because you guys remember we have now period is capital T, so it will be confusing. So let me convert all these to FT instead of T to avoid confusion. This is FT and this is also FT. All right, that's it. That's horizontal uniform circular motion. Here's another one. This is also horizontal uniform circular motion. We have a car taking a turn, so it's going around a partial circular motion, but it's around a circular motion. Speed is constant, velocity is changing always along this. Let me do that green so it will agree with the picture. The velocity is always tangent to. I picked the wrong point here. Let me pick this point over here. Let's say it got in from here. Here we go. Velocity tangent to the circle. Let's pick one more over here. Velocity tangent to the circle, and it keeps changing direction as the car moves. I'm gonna pull this guy a little bit up. And so, all right. The mass of the car is given as 1500 kilograms. The ugly picture is drawn for us here. It's actually a beautiful picture. And the known values are listed. What is the maximum speed with which a 1500 kilogram car can make a turn around a curve of radius 20 meters given on a level means it's a flat, it's a horizontal turn road without sliding? The static friction coefficient is 1. Now, if there is no slide, the friction is static friction coefficient. And in these type of situations, the force that generates this uniform circular motion is always the friction force. And if there's no slide, then it's always a static friction force. And that will be our F net. There's an A towards the center. We take that as positive. And there is no other forces along horizontal here. So we apply F net is equal MA. And V squared over R and solve for the unknown. What is the maximum speed? If we increase speed, the car actually will go and slide off the road, take it off the circle. So we're going to find the maximum speed that it can do the turn safely by assuming that this friction force is equal to F net. If the F net is larger than that, the car can't do a uniform circular motion. F static cannot keep it in place anymore. What is the static friction force? It's always equal to mu static times N. In this case, cars here on the road, only force pushing on the road will be down. We're looking at top view again here, and the side view is shown there. Would be the weight, which is mg, and mg would be equal to N. So this guy is equal to mg. So I'm going to input in the values now. F static is my F net. And that's equal to mv squared over r. That's my net force. And if I have my net force to be this, the car will not slide. If my net force mv squared over r is larger than this, car will slide. So not sliding condition, which is an important thing here, is minimum condition is that F static is equal to mv squared over r. Now what happens if F static is larger than mv squared over r? It can safely turn, but minimum it should be equal. For that equality to hold, we can have a maximum speed. So the net force mv squared over r will not be larger than F static. So we use this equation here. For this equation, V is equal to V maximum. And then we solve for V. I'm going to put in all the values and solve for V. I'm going to have my static friction force, mu s times N, is equal to mv max. I'm replacing this squared over r. Now I'm going to input mg for N. I will have mu s times mg is equal to m v max squared over r. Notice how I can divide each side by m. This guy goes away. And when I solve, I want to leave v max alone. when I do that, I'm gonna have, simply I can carry this guy here. Okay, I'm gonna have V max squared is equal to mu s g times r. And of course I don't want to solve for V max squared. I want to solve for V max. To reach to that, I have to take the square root of each side. So what I'm going to find is the maximum speed my car safely can turn is equal to mu s times g times r. And this is kind of a fixed equation. If I know the radius of the turn, r, right, g, which I know, and if I know the friction, static friction coefficient, I can always calculate the maximum speed that the car would take to turn that corner. Putting in the numbers, our mu s was 1, no unit for mu s, remember, 9.8 meters per second squared, g, and r is 20 meters, right? Was it 20 meters? Yes. And that should give us a V maximum of 14 meters per second. So if you have 20-meter radius, turn around it, you can maximum go at 14 meters per second. Otherwise, you're doomed. Know your physics. Physics, Rex. This is kind of our last question. There are some short ones after this. Similar idea to tension. Remember, we're going to solve for this now. We have a motorcycle stunt, and it goes around this loop-de-loop, and he doesn't fall, or she doesn't fall. With a constant speed. So we have uniform circular motion. Let's show the speed here. V, right? Always tangent to that circle. I'm kind of showing it interior because the guy, the lady or guy is going inside the circle here. All right. The radius of the loop is given 5.5 meters. As I told you before, I like putting numbers on the pictures. It helps me see the situation better. What else is given? No. What is nothing else? Okay. What is the critical speed at which the motorcycle can pass 0.3 without falling? So I have to apply Newton's second law to 0.3. Let me put this here. Apply. You guys know this, right? Newton's second law at 0.3. How do I do it? First, draw an ugly picture, draw for me, show all the forces, well, show all the known values, we did that, show all the forces. Mg will be down at 0.3. N, or Fn, normal force, will also be down because remember, not Mn, let me call this Fn this time. Normal force is Fn, okay? Get used to that too. This is what we called N so far. Also down. And we know uniform circular motion towards the center is always positive because A is towards the center, right? Everywhere. We'll take that to be positive direction. That's positive here, 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 and here. Always towards the center. So in this case then, Mg and Fn or N both are positive. And then I apply Newton's second law. F net is equal to ma, which is m v squared over r for the case of uniform circular motion. And my F net now, I'm going to add all the forces to find my F net. It's the normal force plus mg, and that's equal m v squared over r. Okay, now what I am looking for though is what is the critical speed at which the motorcycle can pass? It's similar to the car taking a turn. For this case of situation, the critical speed is found. For me to feel feel some push on the surface, which is the normal force, my normal force should be larger than 0. But minimum normal force can be 0. Then I have a critical speed. Okay? At least the normal force on me should be 0. Or larger than 0 is also fine. But the minimum is 0. Then I can safely turn from here. Okay? So if Fn is 0, I have critical speed. If Fn is larger than 0, I can safely turn at 3.3. This one I can barely safely turn, okay, but I can still turn. So this will be our minimum safe turning situation with the critical speed. Therefore, if I solve for Fn or n, let me use green again here. From here, Fn plus mg equals mv squared over r. And if this guy goes to 0, the critical situation then tells me that mg should be equal to mv squared over r at least for a safe turn, barely safe turn. Okay? Then this guy is a V critical, I'll call it VC. Or maybe crit so you can see it better. When I solve for that V critical, again, multiply these. You guys know that by now, I'm hoping. So V critical is equal to squared is equal to GR. See how this is similar to what we had in the root case, but I want to solve for V critical. I take square root. So V critical equals square root of G times R. I didn't have to actually know the mass canceled. All I need to know is G times R. In this case, it will be 9.8 times meters per second squared times R, which is 5.5 meters. And that will give me, let me try that again. 5.5. And that will give me a critical speed of, should have it somewhere here, 7.34 meters per second. That's the minimum speed I should have. I could have a larger one. If I have a larger speed, this mv squared over r is larger than mg. I have an Fn that is not 0. That will also work. Even better, even safer. So the larger my speed here, the safer I will turn. The larger the safer turn. All right. So that's part A, solved. Good, clear, 7.34 meters per second. B, oh, I don't know why I said B and C. It's A and B, okay. B asks me, assume the driver goes around with this critical speed. So assume it's always keeping the critical speed, okay? Constant. And it's, what did we find it to be? 7.34 meters per second. Find the normal force at point 1, 2, and 4. At point 3 with this critical speed, n is 0, right? We found it already. That's the bare minimum for velocity, and that's what we solved for. So at point 3, let's put it here actually, we already figured that n should be 0 for this critical speed. If that is equal to v everywhere, what is n at point 1, 2, and 4? I'm going to do 0.4 and 0.2 first because these are easy points. If I look at there and show my normal force, here's my normal force. And guess what? Along the direction of A, that's the only force I have, and that's my F net. Okay? Normal force is F net only here. mg is down. There's friction keeping the object up. Let me use red for mg. I'm not interested in those. I'm interested in horizontal forces, which is only F n or n. I'm gonna put n actually. This is not net force, okay? This is normal force. Net force I will always call F net, like in here. So along here then, F net is equal to normal force. F net is always mv squared over r for a uniform circular motion. That's equals to n. The same thing. One is to the right, one is to the left. Both are positive because we are taking towards the center positive everywhere. And I'm going to solve for that n. Guess what? I know everybody. My v is v critical. I know r, I know mass. I can solve for my n. So n is equal to the mass times... Oh, do we have the mass? Not given. Let's assume driver has a mass of 65 or 95, I remember. I believe I used 95 for the solution. I forgot to edit here. So 95 kilogram driver with the total mass, driver with the motorcycle and so on. So 95 kilograms. Let's redo this together to make sure I have the correct number here. Velocity squared for 7.34 meters per second squared divided by r. 5.5 meters, not 2. I have a number here, but I'm not sure if I use 65 or 95 kilograms. So let's solve this for 95 kilogram together to make sure. So I'm going to do this in here. What do we have? 95 is our m, right? Times the 7.34, our speed, minimum speed squared, divided by r, 5.5. 930.6 Newton. That's our answer. 930.6. Let's put 2 decimals. Was it 5.6? Let's check that again. 5.7. So I'm gonna put 2 decimals. And it's the same at 4 and same at 2. Okay, now we're going to do 1. What is the normal force at 1? That is a bit more interesting. If I look at 1, normal force is upward, as always, perpendicular to the surface. mg is downward, as always, right? And towards the center is always positive because A is towards the center. So N is positive here too, but mg is negative. So if I want to write down F net is equal ma for 1, I'm jumping to mv squared over r for ma. So I'm hoping you guys are on board with that. Ma is always mv squared over r for uniform circular motion. And F net now is n minus mg. That's equal to mv squared over r. Guess what? To solve for n, I take this guy to the other side. It goes as plus or added to both sides, whatever, the same thing. I will have n, normal force, is equal to mv squared over r plus mg. Go ahead and solve that. You should find about 1682 Newton force. All right, these were very important types of horizontal circular motion. Again, as I've talked before, there are other versions, but idea is always the same. F net is equal to ma. A is that guy, v squared over r, so F net is equal to mv squared over r. Our cars could be turned along a banked road. Then we have this situation here. Assuming friction is zero, no friction. There's a centripetal force towards the center, which is a component of the normal force. And we know how to find this normal force, right? It's mu s times, not mu s times, sorry. It's, in this case, is m g cosine theta. This case we already discussed. This is Tx, and that's equal to F net is equal to ma. If there was a friction here, since the car want to go out in this direction, the friction would be in this direction. And the next question is discussing that. Show the forces. It doesn't say no friction, so we will have the friction force will be static friction. We will have mg. And we will have normal force. That will be our answer. That's it, my friends. I will see you in classroom. Actually, I want to tell you a little bit quickly about this too. Sorry about that. Apparent forces. We all know that as our car goes around a curve, we feel a push outward, as if somebody is pushing us outward, but we know there is a force towards the center. So what happens here is that due to inertia, we were going straight here. We're going to keep going straight, but we're pushed by the car's door with a normal force. So we're feeling like we're pushed towards the car, just as if when we stand on the floor, we feel the push upward. We feel this normal force by the car's door. Similar things happens here. What we feel is the normal force. And if we want to calculate our apparent weight here, apparent weight would be the normal force. And we learn how to calculate the normal force. Because there's acceleration, there are different situations, just like we were calculating apparent weight in an elevator, the same situation holds here as well. And this simply goes over how we can find the critical speed again over a loop-to-loop, so nice summary here. For a safe turn, and should be larger or equal to 0. If it's 0, we have critical speed, and we can solve for that. Then we will always find this value. So keep this as an example, or how to find the critical speed for this case here. Centrifuge uses the idea of apparent forces to separate components in a liquid. This is used in medicine a lot for separating blood particles and having the blood plasma separated. If we rotate the liquids in a centrifuge, stuff will be pushed outward, and larger masses has larger inertia, so heavy mass will be at the end. More a solid part, and liquid part will be more towards the center. You can also try to see the feeling of the centrifuge. If you rotate your arm and keep rotating, the blood will be pushed towards your fingers, and you can feel and see that if you see your blood vessels pumping up a little bit more on one hand than the other. All right, now it's all over. That's all I want to tell you now, and I'll see you in classroom.